Has a Ph.D. in environmental engineering from TU Berlin. He worked for 5 years with a consulting engineering company in several international wastewater treatment projects, which were focused on water reuse. And now he's been appointed full professor for sanitary engineering and water supply at Münster University, Germany. And currently he is the spokesman of the working group on water reuse of the German Water Association. So Jens, now the floor is open for your presentation.
Thank you very much, Jiri. Do you see my presentation?
Yes, I can.
Perfect. Thank you very much. So, as Jiri Vanna already said, I will give you a brief overview of technologies which are suitable for water reuse. I will just say a couple of words about the background of what I'm presenting, and then I will jump directly into consideration of technologies which are appropriate to achieve the water quality required for water reuse. I am giving this presentation as well on behalf of our DWA working group on water reuse. DWA is the German Association on Water, Wastewater and Waste. And our working group on water reuse is one of more than 350 specialist groups within DWA. And we are, currently we are around 15 experts from different institutions. And I won't go more into detail, but as you see, Dr. Lahnsteiner is also a member of our group, and he will give a presentation on case studies later on. Besides the definition of technical standards for wastewater treatment, especially focusing on wastewater treatment, DWA also publishes a more or less loose series of so-called DWA topics dealing with different issues in terms of water management and water treatment. And our working group has published a topic on treatment steps for water reuse in 2008, where a variety of different treatment technologies were characterized and assessed with regard to non-potable water reuse, focusing on irrigation. It was published in a couple of languages, and just last year we published completely revised and largely extended version of this volume called Non-Potable Water Reuse, where we give general guidance for planning and expanding projects that are dealing with non-potable water reuse. So it shall be helpful for planners, but also for operators and authorities. The focus of this volume is on the use of recycled municipal wastewater as a substitute for fresh water, focusing on agricultural irrigation, but also urban landscape irrigation and other urban and industrial uses. And I will come back to this volume in a couple of minutes. But now let's have a look on treatment technologies, which is the main topic of this presentation. When we're talking about water reuse, we have to be aware of certain hazards which are related to the water quality. So the hazards related to water reuse are due to different types of wastewater constituents. First of all, there are microorganisms or pathogenic microorganisms and parasites such as helminths, protozoa, and of course pathogenic bacteria and viruses. But besides these organisms, there are also certain inorganic substances which are usually contained in wastewater in more or less high concentrations. inorganic substances such as heavy metals or also borate, which can be impacting the plant growth. On the other hand, there are also certain organic substances such as household chemicals or pharmaceutical residues, which also have to be kept in mind when reusing water for irrigation. But until now, there isn't yet very clear knowledge about the impact of these organic substances. And finally, we have to keep in mind the salinity of the wastewater, because salinity affects the structure of the soil and therefore also the soil fertility. So we have to protect, on the one hand, the environment, and on the other hand, the public health. That means the users of the reclaimed water, so the farmers, the farm workers, but also the consumers of the produce, and also residents and the general public, which might get in contact with the reclaimed water, for instance, via inhalation of aerosols when passing by irrigated fields. The most imminent or most immediate risk in the context of water reuse is related to pathogens. And as you see here are just a couple of famous examples. So Ascaris lumbricoides is a very popular helminth. Giardia lamblia is a widespread protozoa. And of course, E. coli and viruses are also always contained in wastewater. So when we are talking about water reuse, the main focus in terms of treatment is on the removal of these types of pathogens. Here you see a very simplified, pretty much simplified schematic of a conventional wastewater treatment plant or treatment scheme, which nowadays usually includes so-called secondary treatment. That means there's not only the mechanical removal of certain wastewater constituents, but also the biological or biochemical removal of organic substances, which might consume oxygen in the river, and also of nutrients. And usually the secondary effluent deriving from such a conventional wastewater treatment plant is discharged into a receiving water. Usually it's a river. But when we talk about water reuse, well, we have to somehow deal with the secondary effluent deriving from the conventional treatment plant. And this means that we need additional measures in order to keep the quality, to achieve the quality required for water reuse. So we need some kind of advanced treatment and, of course, a certain storage and distribution system which should not negatively impact the water quality, of course, before it is reused. So as you see, there are two main parts of this system, the conventional treatment, which is also considered in the new EU regulation as the wastewater treatment. And then there's the further water treatment or advanced treatment in order to produce a higher water quality. The advanced treatment, which I will now focus upon, can only be one component of a multi-barrier system. That means that advanced wastewater treatment is a very important step towards minimizing the risks for workers and consumers, but it can only be one component of a multi-barrier protection system. So also the irrigation technology, for instance, or the irrigation practice are also important in terms of risk management. So in this diagram, you can see typical concentrations or ranges of concentrations of microorganisms contained in wastewater. This refers to fecal coliforms. And as you see, during the conventional or so-called conventional secondary treatment, the concentration of these bacteria is only decreased to a very slight degree, so by 1 or 2 orders of magnitude. And even an additional sand filtration leads just to a slightly further removal of these microorganisms. If you consider the requirements of the new EU regulation, you can see that none of these treatment steps leads to to keeping these limits. And this can only be achieved by an additional disinfection, and this is what I'm going to be talking about right now. So, disinfection of secondary effluent can be achieved by different means, by different types of or categories of technologies. First of all, there's the physical separation of pathogens, which can be efficiently achieved by membrane filtration. I also added sand filtration and microscreening, but I put it in brackets because, as you already saw on this diagram, sand filtration does not lead to the removal of bacteria and viruses, and the same holds true for microscreening. But sand filtration and microscreening can remove protozoa and helminth eggs. Then there is the use of chemical disinfectants, which can be, besides chlorine gas or chlorine dioxide, also ozone, peracetic acid, and others. And finally, disinfection can be achieved by the use of electromagnetic radiation. That means this is usually UV radiation. So let's have a closer look on these different types of separation or disinfection processes. On this diagram, you see the different size ranges of the microorganisms or the organisms I'm talking about. So protozoa and helminths are not shown here, but they are usually between 10 and up to 100 micrometers in diameter or in size. Bacteria usually have a size around 1 micrometer, and viruses are much smaller. So when we try to physically separate these microorganisms from the wastewater, we can use low pressure membranes, which include ultrafiltration and microfiltration membranes. And the pores of these membranes are so small that not only protozoa, helminth eggs, and bacteria are efficiently retained, but also partly viruses, which are often attached to other particles. A drawback of the very efficient, indeed, membrane filtration is that it has increased demands in terms of energy input, of pre-treatment, as well as of operation and maintenance. Sand filtration is a quite cheap, or let's say cheaper, alternative for the removal of protozoa and helminth eggs. But as you already saw on the previous slide, bacteria and viruses cannot be removed by sand filtration. So in order to achieve efficient disinfection using sand filtration, another disinfection step has to be added. This is usually UV disinfection, or often. And in terms of microscreening or microsieves, the removal efficiency is quite comparable to sand filtration, of course, depending on the mesh size of the microsieves. But there's one, let's say, neuralgic point in terms of microsieves. The removal efficiency is not only defined by the mesh size, but also by the integrity of the sealing of the microsieves. So the microsieves are attached to some kind of supportive structure, and from time to time they have to be removed and cleaned, physically cleaned, and then be put back again. And with time, this sealing suffers. So this the experience has shown that this often is well quite crucial part of the system. Then we come to the chemical disinfection. This is just a general diagram showing the effectiveness of chemical disinfectants, for instance, chlorine, as a function of the dose, so the concentration and the contact time. And as you see, if you use just a very low dose of chemical disinfectant, the efficiency is also very low, because much of the chemical is first of all used for reactions with dissolved substances and not for killing bacteria or other organisms. Then with increasing dose, the efficiency increases, and usually in terms of wastewater disinfection, a certain plateau, a certain constant level is achieved, where there's no further increase of the effectiveness, because some of the microorganisms are usually attached to particles and they are shielded by particles. So the more particles are contained in such a secondary effluent, the more complicated it gets to achieve a high disinfection efficiency. So very famous chemical disinfectants are chlorine gas, of course, and also sodium hypochlorite. The disinfection efficiency, both of them, is based on hypochloric acid, and therefore it is only efficient at pH below 7.5. During the reaction of chlorine gas and also sodium hypochlorite in wastewater, it reacts with a lot of other organic and also inorganic compounds, resulting in the formation of harmful disinfection byproducts, which are harmful not only for the environment, but can also be harmful for the people, for human beings. Use of chlorine gas is hazardous for plant workers and also for the public, as repeated accidents unfortunately show. But chlorine gas is quite cheap compared to other disinfectants, and it has a big advantage in terms of a residual disinfection capacity. So the disinfection capacity can be kept or is kept during the storage and distribution of the treated water, of the reclaimed water in the system. Chlorine dioxide may be an alternative for use of chlorine gas. It has a higher disinfection efficiency in terms of protozoa, because chlorine gas or chlorine has a very low disinfection capacity with regard to protozoa such as Giardia lamblia. So chlorine dioxide is more efficient. It is independent of pH. The disinfection byproduct formation is lower, but it has to be generated on site because it is an unstable gas. The same holds true for ozone. It has also to be generated on site, but it has also a very high or even higher disinfection efficiency. A disadvantage is that ozone has no residual disinfection capacity because it quickly gets consumed in the water. And there's also the potential formation of disinfection byproducts to be considered, especially bromate and nitrosamines. Finally, UV disinfection. UV disinfection is based on the inactivation of cell structures or cell processes When UV radiation is absorbed by DNA at a certain wavelength, around 260 nanometers, well, some reactions happen that should not happen in our or in the bacterial DNA. So there's a cross linkage of certain components of the DNA leading to the inactivation of the organisms. The efficiency of UV disinfection is strongly depending on the concentration of suspended solids and also of the transmittance of the solution. So it is strongly recommended to have concentrations of total suspended solids below 20 milligrams per liter, preferably below 5 milligrams per liter. And therefore, the combination with the previous filtration stage, such as sand filtration or microsieving, can result in a higher efficiency of the UV disinfection. In order to achieve an efficient disinfection, you need sufficient irradiation intensity under controlled flow conditions. Here you see an example of a wastewater treatment plant in Berlin, Germany, where the water flows through channels, and in these channels you see the UV lamps. So the water flows around the UV lamps, and the organisms get killed. A big advantage of UV disinfection is that there's no disinfection byproduct formation, but since UV disinfection also does not have residual disinfection capacity within the network, there might be the regrowth of microorganisms surviving this disinfection step. So keeping the time in mind, I will just quickly jump back to our DWA topics on non-potable water reuse, where we considered a variety of treatment processes for protection against pathogenic organisms, well, in detail. And we developed an assessment matrix in order to provide a fast and also quite simple support in order to get or to take a decision for a suitable combination of treatment technologies, focusing on subsequent water reuse. In this assessment matrix, we considered 27 different mechanical, biological, and advanced treatment processes, and we evaluated them with regard to 44 assessment criteria in terms of health risks, economic efficiency, effects on the environment, but also requirements on the operating personnel and plant and irrigation technology, and always focusing on the type of use. So an important point is that the type of use has always to be kept in mind in order to produce a water quality which is fit for purpose, for the irrigation purpose or purpose of reuse. And as I said, this decision support, or this should be a decision support, but only as a basis for further, much more detailed site and plant specific investigations. What you see here, this kind of traffic light matrix should only give an overview about the general structure. The matrix is much more detailed. This is just an excerpt for physical treatment processes, and as you see here on the left side, there are the assessment categories, which are then evaluated either qualitatively or quantitatively, and also always giving the source of the data. You can get this the entire assessment matrix free of charge via the website of the DWA, and as Mai said in the beginning, you will get the slides tomorrow, and there you will also have this link. So to conclude, you don't have to be a prophet, I guess, to forecast that water reuse will become more and more relevant against the background of climate change. There is a variety of state-of-the-art technologies available in order to provide the water quality that is required for water reuse, for safe water reuse. But it is very important not only to focus on advanced treatment, but also on the conventional treatment. That means the secondary treatment, because a stable secondary treatment is the precondition in order to achieve a reliable efficiency of the subsequent advanced processes. And as I said, treatment, water treatment, can only be one component of a comprehensive multi-barrier system. So finally, well, our DWA topics on non-potable water reuse, they consider these different treatment technologies quite in detail, but beside this, you can also get a further overview regarding regulatory, ecological, socio-economic, and energetic aspects related to water reuse. So, thank you very much.
He is a full professor at the Lisbon University in Portugal, where he is teaching water supply, urban drainage, and water quality courses at master and PhD level in the civil engineering and environmental engineering section. He was involved in hundreds of water management and water reuse projects in Asia and Africa. Currently, he is the president of the Civil Engineering, Architecture and Geo-Resources Department of the Lisbon University. And at the same time, he is the president of Portuguese Water Partnership. So, José, please, the floor is open for your presentation. Can you hear us?
Okay. Are you listening to me?
Yes, perfect.
Okay, okay. Thank you very much. Thank you, G. Dear colleagues, dear audience, good afternoon for all of you. It's for me an honor to be in this event, to be in this webinar. You are a little bit late, so I will be a little bit in a hurry, but you will have all these presentations tomorrow, so all the slides tomorrow, so you can afterwards confirm the information that is in there. This will be a very practical presentation. It relates with the water reuse at the city scale, the case of Lisbon, Portugal. So I was born not in Portugal. I was born in Mozambique, in Africa, but I live in Portugal for more than 50 years. So this is the table of contents, introduction, objectives and guidelines, potential of water reuse. I will do a quick view of that. Quality requirements, water sources for the Lisbon city, potential consumptions in terms of water reuse, design criteria for the water reuse system, proposed solution, phasing, preliminary design, investment estimate, final consideration. So it's a very, it's like a case study. So this is based on a strategic plan that I've been involved in the water reuse for the Lisbon city, that was developed just 1 year ago for Águas do Tejo Atlântico. Is the utility that manages the wastewater system in the Lisbon area, not just in Lisbon, but in all the area, Lisbon and surroundings, for more than 2 million people. Lisbon itself has more or less 500,000 people, not counting with, of course, with tourist contribution. The objective of this master plan of this and of the municipality and of the utility was to have all the urban cleaning and all the irrigation of the parts of the city supply by water reuse by 2030. This was the goal. Of course, that the benefits of water reuse, you have the social and environmental benefits, releases drink water essentially for human consumption. You see that the water coming from the drinking water of Lisbon is coming from Castelo de Bode Reservoir, about 140 kilometers far from Lisbon. So it's a long distance. So it's really so this is the reservoir of Castelo de Bode with this large pumping system, the dam, the water treatment plant. So for the water arrive to Lisbon, it consumes a lot of energy, a lot of chemicals, a lot of materials have been involved on that, a lot of human resources for operation maintenance. So it means that for some time of uses, the supply of reused water is crucial. And of course, that with the wastewater, you will have natural fertilizers and don't depend on climate uncertainty. Portugal is very prone to the effects of climate change, not just the sea level rise, but also in terms of precipitation. So you are in a kind of Mediterranean area. You have a lot of months, 3-4 months without raining, even in Lisbon. So it means that makes all sense this type of project. This is the uses that you are planned for the Lisbon city. So you have the irrigation. It will be the main use. Well, I would say that at least 2/3 of the water use is for irrigation, but also for cooling, also for sweeping of collectors, washing roads, and so on, and also some recreational and environmental use. So all these type of uses will be applied. Concerning the availability in Lisbon, you have three large wastewater treatment plants. The major is Alcântara. That serves not just Lisbon, but also some municipalities in the surrounding. So you have 3 in the west part, Alcântara, in the east part, Beirolas, in the central part, Chelas. And we can see that on average, you have enough water from the treatment plant to the consumptions. So, of course, that even in peak consumption for the irrigation, as far as you have storage, local storage, you have capacity for all the water uses. So this is in blue is the wastewater flow available from the wastewater treatment plant of Alcântara. In red is from Beirolas, and in green is from Shell. So it means that the critical factor is not the quantity, the critical factor is the water quality. So, of course, that at the time we have developed this master plan, the European regulation was not approved, but even so, the draft was available. And in concerning this master plan, this strategic master plan, it was aligned with, of course, with the figures and with the requirements of that regulation. So some information about serves a lot, not just Lisbon, but a lot of municipalities. Is typically we have combined sewers, separate system, partial separate system sewers. This is the average flow depending on the month of the year, and it treats the wastewater of 2/3 of the city, about 600,000 inhabitants. The Alcântara is very well known because of this large green roof. That is, I think, that is the biggest in the Iberian Peninsula. It's 4 hectares of green roof. So this is Avenida de Ceuta, is very well known, and nobody fills the wastewater treatment plant. So it's a modern treatment plant. And you have some of the works have already been executed. So it means that downtown, the piping for the reuse and some uses are already been into place principally for washing roads. It means that this water is being reused for cleaning the roads, and so we save the water coming from the water of good quality, of great quality, coming from Castelo de Bode. And of course, you have also not just pipes, but storage, pumping installation, and so on. This is the other system. In the east side is Beirolas wastewater treatment plant, and mainly you have mostly combined system also, but the average flows are a little bit lower. But even so, there are also a lot of just close to the treatment plant is the Expo, so there are a lot of parks, gardens that can be also you can also use this water for use for irrigation purposes. One thing that is interesting is that in Lisbon you are preparing, well, in fact you have prepared, and the tender was being launched some last year for the construction of two big tunnels. These two big tunnels, large tunnels, is 5.5 meters diameter at least. It's just for controlled flooding. But these tunnels cross the city. There are two tunnels crossing the city, and you will use these tunnels just as a mean to transport along the tunnels. There are here in the invert. There are here. You put some pipes, a pipe, 300 millimeters pipe, just for transporting the water from the treatment plant, and to deliver in certain points along the city in order to facilitate the transit. Well, the data, all this data was being delivered by the municipality. It was reference data concerning all the historical documentation about the water consumption in different points of the city. So all this information was provided. With all that information, and also with the planned works for the next 10 years, you have used all that for computing the consumptions, the needed consumptions of the future. Of course, you have more than 40% for green areas, but you have also a good share for streets washing and for the different other purposes. And this is just irrigation. Each park you will have at least 6,000 cubic meters per park per year that you need, with some peak consumptions. All that has been introduced, and water for urban cleaning. All that was introduced in the hydraulic model, just to design the pumping systems, the storage, and the pipes. Of course, there are some principles. The definition of the routes. Sometimes when you have the underground infrastructures with available space, you use it to put the pipes that without disruption of the surface, of course. And in other situations, you have installed the reused water pipes below the drinking water infrastructures and above the wastewater sewers with a minimum distance, in order to ensure protection against a certain kind of protection against contamination. So all these cares have been taken. So this is very typical design criteria for the pipes, and for the velocities, very typical, 0.3 for gravity mains, 0.6 for the case of the pumping systems, maximum velocity of 1.5 meters per second. So it's typical of water systems that you have used also in that case. Of course, the storage, the local storage volumes were taking into account the peak consumptions also. Of course, that when emergency situations prevail, the tanks may be supplied with, of course, with water from the public network. Okay. And there are, of course, a non-return valve in order to maintain the risk of contamination of the public network. So all this has been taken into consideration. And in master plan, three phases have been planned. A short-term phase, so you have the storage volumes, just 2 storage volumes, but 5 pumping stations, a lot of pipes, the areas to be irrigated, the volume planned for the volume of irrigation for each year. So this is defined well in this map, and a second phase between 2001 and 2003, and the third phase between 2003 and 2025. So all of this allows, if this program will be accomplished, I'm not sure because of this crisis of the coronavirus, the works have slowed down a little bit. But I'm thinking that after all these pipes, all these pumping systems, all these storage rooms will be in operation, the great majority of the city will be served by this system. So this is so you have here a network of pipes and with some pumping installations with a lot of storage volumes. So it's more than 50 kilometers of pipes, more than 12 storage volumes, I think about 20 pumping systems, and you just cover the great majority of the city. So this is the timeline. I will just jump. This is the number of pumping installations, 15. And of course that you have needed to use the hydraulic model, and you just use the freeware AppNet developed by EPA. That is very it's very well known in the world. A lot of people use it, and of course you have done a lot of simulations for different scenarios for the phase 1, 2, and 3. And with these simulations, you were able to, of course, to design the pipelines, to assess the pump flows, the head losses, the pump heads, and optimize the volume of the storage tanks. Now, is that just an example with the range of velocities all along the main? Of course, this is just the main pipes, the main trunk pipes, and the investments cost you estimate is not so much. It means that, well, this is of course you have a lot of infrastructures, but because some of them are of very small diameter, the sum of investment as planned in 2018 or in 2019, it was less than 20 million euros. So it's not a really very high cost. This is the global investment. So in red is the total, but you have 3 subsystems that, if there are the areas that are served by each one of the 3 treatment plants of Lisbon. Of course, that you have also estimated operation maintenance costs, but I will not just present that concerning operation costs. Just to finalize, I would say that this strategic plan is being carried out in 3 phases. The water will be supplied by the 3 wastewater treatment plants of Lisbon, Alcântara, Barros, and Chelas. Includes the construction of about 55 kilometers of water mains, 16 pumping systems, and 12 storage tanks. The irrigation are not so well. You have not a lot of parks in Lisbon. It's less than 200 hectares of green spaces, but all of them will be irrigated with this water. This water from the treated effluents of the wastewater treatment plants, and over 1.2 million cubic meters per year. And this is the investment. So I think that this is alternative water source that will make Lisbon city more sustainable in respect to water, no doubt, more resilient, and better adapt to climate change. So I think that is something that you are pursuing at the moment, with the involvement, of course, the deep involvement of the municipality of Lisbon and of the Águas do Atejo plant, that is the utility that is managing the wastewater treatment plants. Okay.
Our next presentation will deal with the public perception of water reuse projects, which is crucial for the success of the project. And the presentation was prepared by Dr. Eileen O'Neill, who is an environmental scientist with over 30 years experience working on water issues. Before founding her own company in 2019, she was the executive director of the Water Environment Federation, one of the world's largest professional association for environmental scientists and engineers, which is also the organizer of famous WEFTEC. So, Eileen, if you could hear me, the floor is open for you now.
Okay, and I'm assuming everyone can see my screen.
Yes.
Yeah,
Yes, good. Thank you. Thank you, everyone. It's really an honor to be here. I am based in the United States, just outside Washington, D.C. And we're going to take a bit of a step back, looking at the bigger picture of what we've learned from decades of working on water reuse in the U.S. I'm working on a paper with some collaborators. Obviously, any errors here are mine, but I'd like to acknowledge the contributions of some people who have a depth of expertise in water reuse. Melissa and Kristen, pictured her on the slide, are working right now with an innovation and workforce development center just outside Atlanta. And I'm on the board of that organization, but both of them have histories working with the Water Reuse Foundation and the Water Environment and Reuse Research Foundations. And the other person that I have been working with is Rick Warner. He is right now with the Nevada Water Innovation Institute, but previously he was with an agency in Reno, Nevada, and is a past president of the Water Environment Federation. And one thing in the US, in many, many states, the water and the wastewater systems are managed separately. And nationally and often at a state level, they're governed by separate legal frameworks and often different agencies. And one thing I learned from Rick, since the Water Environment Federation is primarily comprised of people who work on the wastewater, stormwater, and water environment issues, is that we are not going to advance water reuse by working on our own, that we have to do it within an agency, with an organization, and even at an individual level in collaboration with our colleagues on the drinking water side. So just acknowledging my colleagues there, and there are web links to their organizations. We heard that it's about 2.4% of wastewater generated that's reused, I think on average in Europe. The numbers, the volume, US is always at the top of the charts. We have potential to achieve more. In 2009, the US population grew by about 50%. But if you look at some of the warmer, drier states, Nevada, Arizona, Florida, Texas, and California, you see the growth is much greater. But like others, climate change and population growth are part of it. I think there's increasing need for and competition between different sectors, but we see this across the United States. I think in a survey, 40 of 50 managers, water managers for different states, said they see potential for water shortages within the next 10 years. And so people are looking to water reuse as a potentially more secure water supply source. We talk about water security or water sustainability. We've got quite a lot of experience in the US. I'm just going to move on in the interest of time. We've been using reused water for irrigation. I think the earliest use, it's definitely in the 1920s. I don't know if it was as early as 1926, but as soon as about 2000, nearly half of the water produced in California was used for agricultural reuse. We also have seen a strong reuse in Florida in terms of agricultural and landscape irrigation, and even more trends that way because of the stress of population growth on water supply. We also have seen indirect potable reuse in the US. There's a very famous groundwater replenishment scheme where water has been reused, drained into the ground, reused water to offset saltwater intrusion into the groundwater as it is pumped out for water supply. I'm sitting in Fairfax, Virginia, and within about 20 kilometers of me, there's a much less famous project, but where surface water for a drinking water system is being augmented by discharge from the Upper Occoquan Service Authority, basically, and has been since 1978. Of extreme emergencies of water supply. There was the wastewater was effluent, was retreated several times in a treatment plant and used for water supply. And we had in the 2013 era with drought in Texas, West Texas, and we had water being reused for direct potable. And we now have some planned systems. I think the El Paso, Texas is going to have maybe, I think it's for about 36,000 people, water supply from potable water supply from reuse. And obviously we've had an experience with industrial, and something that I find interesting is how people are also thinking about, can we reuse water within a building, within an urban location? And there are examples from the early 2000s in New York City where some luxury apartment buildings are reusing within the building water for toilet flushing and heating and cooling purposes. And in San Francisco, in certain areas downtown, either new or highly renovated buildings must include a reuse component. So that's interesting to me to see that on-site being nested, if you like, within a centralized system. Overall lessons learned in terms of the softer skills, I think leadership, collaboration, and public engagement are some of those buckets or groupings of what we used to think of as soft skills. Obviously, when we listen to what sort of systems are being implemented, both on the treatment side and the monitoring side, we actually have to have high technical competence, and we have to demonstrate that so that the public believes that these systems are safe. And there's a couple of subcategories within that. Leadership, yes, we're willing to be the first to implement such a system. The Monterey One Water system, I know that manager there said it'd be very easy for a board to say this kind of approach to do on a voluntary basis. It would be very easy to say this is outside our scope. This is not what we do. And I've got the University of South Florida down there because a colleague of mine actually, who's an engineer, actually did his PhD looking at what are the success factors in utilities that are moving towards a much more sustainable business model. And the number 1 and 2 factors that he came up with were a champion at the utility level in terms of the CEO and a political body willing to support that. And not so far away from me is the Sustainable Water Initiative for the Future, the SWIFT project. That is a wastewater organization that has proposed and is implementing groundwater recharge through treated wastewater. And when you ask how did that come about, they say, well, we have a visionary manager who thinks that the best thing to do here is not to remove nutrients and treat the wastewater to an extreme level that is currently required. Through collaboration between the sanitation district that produces the effluent and the water agency that is a wholesale supplier of water in California. And this in the middle is a limited edition bottle of reclaimed water that was used for a celebration. But these two organizations have worked together. I think it was the initiative of the water organization, but they then co-funded the project. It over time enabled the wastewater department not to have to build a new ocean discharge pipeline. And so collaboration over decades has been key to the success of that project. And you'll hear some of the larger projects that there'll be a wide variety of agencies that need to be able to work together and in a way that perhaps is not something they've had to do in the past. Just to remind ourselves that these are, as we've heard, these are complex systems and one does need high technical competence. It's the ability to innovate, use innovative technologies, but also guarantee that operational reliability. And review of that has indicated having a highly skilled and a flexible workforce that can move with changing times, but also an organization that commits to research and learning as being key factors. One thing that I know that the Orange County Water Department is particularly proud of is their state-of-the-art monitoring lab that handles hundreds of thousands of analysis on about 20,000 samples a year, and is taking samples from various places and sharing that information. So an example of where you need skills. And the wastewater treatment operator, or the treatment operators, also perhaps need a higher level of skill than they have in the past. And as I said earlier, we have separate systems in the US for the wastewater and the water system. So the certification happens at a state level, and it is different bodies that certify the water operators, the water treatment operators, and the wastewater operators. So we need to think differently and think about operators that can handle these kind of treatment trains, that can handle the risk management components and the monitoring. And the bottom right-hand side of the scheme is a collaboration between a professional organization for water operators and for wastewater operators that are working together to develop an advanced water operator certification that will be on a voluntary basis, but it is designed to support operators that can have skills to operate both. We also see in the upper right-hand corner kind of high-level collaboration between utilities. The logo there is for the Leaders Information Forum, for Innovation Forum for Technology, and we see organizations working together to fund pilot studies to reduce the cost and the time required for implementation. And some organizations are working directly with universities. The SWIFT program that I talked about, that is down further in the south of Virginia, their director of innovation is also a professor at a couple of universities, and you'll see that many of their projects, they're working with PhD students embedded on site doing research. So high technical competence is a given. To come back to actual public engagement, this is, I think, for me, it's been a very interesting process to see involved. And I think the issues in public engagement is that here in the US, we had some really hard-earned lessons. And we learned that you have to start early at the problem-solving stage, saying, here's the situation we're dealing with, and looking at what options might help us. One needs to cultivate media and public interest and think about broadly what other stakeholders does one need to involve. We have to think beyond, well, we're going to tell the public what we're doing, we're going to inform them. Once they understand, everything's going to be okay. No, we need to listen, and we need to respond when we get that public input, and we need to involve them. And demonstration projects and expert panels have been very helpful, but we're not ever done with this. This is something that continues to need to be addressed. In terms of the hard-earned lessons, it was LA being Los Angeles, there was a water reuse project that was shut down in 2000 by public opposition. And this is where the toilet to tap terminology, and you can see the cartoonists and some of those in opposition really had a field trip day. Here's a headline from the Los Angeles Times from about that time: potential engineering triumph turned PR disaster. And in 2007, the mayor of San Diego actually vetoed a pilot study. And back to what have we learned from that? We've learned that one needs to engage the public often and early. And one of my favorite quotes, so one of my favorite lessons actually comes from Australia. Sue Murphy, who's an engineer, but she's the former chief executive for Western Australia Water, that includes the city of Perth. And she said, as engineers, we're trained to bring the solution, to solve a problem. but we'll get a lot further with the public if we begin with the problem and bring them along with us to the solution. And there are some good information there. This marketing non-potable water recycling is not, it's much more than marketing. And I was surprised to read that and to see way back in 2006, they were talking about starting early and building that time into your project to involve the public. And this schematic here is from San Diego, their Pure Water project, and they have really embraced cultivating and engaging the public. And here's some of the things that can be done. Forming advisory groups, involving environmental and citizens groups, invite the public and the media in, go where the public is, attend community events and briefings. And one thing that Orange County says is have your staff, you need to be trained to communicate with the public, but have your staff be the face of the program and don't stop. And San Diego has really, the Pure Water program there has really embraced that and spends an awful lot of time engaging with the public. This actually is one of the Pure Water Working Group. It's comprised of citizens and environmental groups and business leaders that actually provides input to the Pure Water project in San Diego. So I can't stress enough that it's not a one-way communication, it's involving the public. And when I was reading about this, I thought about something that I've read in the medical field or in legal fields, procedural legitimacy. It's when those in positions of authority come up with a specific outcome or a decision, it's much more likely to be well received if it's perceived as fair. And here's some of the components of success in procedural legitimacy: having a fair process, being transparent, provide the opportunity to have a voice, and be clearly impartial in your decision making. And it struck me that that's a term for us to think about in the water field, being perceived as legitimate. Another couple of important things is the demonstration. That's me up there having a drink of the water produced by the SWIFT pilot system there with the head of the agency. And that's one of my colleagues, Rick Warner, having a drink at the end of the Orange County system. So pilot and demonstration facilities can be very helpful. And many agencies are using independent not just involving the public, but having independent expert panels to advise them, again, to that perception of legitimacy and competence. So I've moved very quickly through that, but you'll have my slides, and Mywood knows how to get me. This picture is from San Diego, and you can see the pole down there. They turned that problem in 2007 of not even having the mayor's support to a system that is going to supplement their, I think it's about a third of their supply by 2035, and they're using it to actually enhance the reputation of San Diego from the green, from the sustainability perspective. And they've increased the public and political support, and many of these organizations, as we know, are getting awards and external endorsements. So it's possible to turn the situation around through these steps. And a recent poll about a year ago now, the survey respondents in San Diego actually were saying we're ready to go. We believe this is what's appropriate for San Diego to purify wastewater, drinking water standards.
Last presentation, which is prepared by Josef Lahnsteiner, who is he holds the Ph.D. in biotechnology from the Vienna University of Natural Resources and Applied Life Sciences. For more than 35 years, He's been involved in a wide range of water and used water and water reuse projects. Currently, he is the director of the technology and the R&D group in the company WABAG group in Austria. He's been a member of the Namibian project, the famous Windhoek-Horenschap direct potable water reuse project since 2005, and he has a lot of experience from this international project. Currently, Dr. Lahnsteiner is the chairman of the International Water Association Water Reuse Specialist Group. So, Josef, please, the floor is open for your presentation.
Thank you, José. Can you see my presentation?
Yes, I can.
Okay, thank you. Just a moment. First, the outline. I will give you a short introduction. Then I will talk about urban and environmental reuse in Egypt and Saudi Arabia. And then I will address industrial reuse and recycling in India. Then I will talk about potable water reuse, indirect and direct potable reuse projects, and then I will draw some conclusions. The drivers for water reuse and recycling, José and Eileen addressed it already a little bit, are of course water shortage caused by climate change, population growth, urbanization and industrialization. Economic reasons are of course a major driver. Used water or wastewater is a drought-proof resource, and there is a boost in water supply security. Water risk is also a business risk, or in case of drinking water can be also a political risk. Major drivers are of course also policies, regulations and guidelines. Here she addressed the new EU regulation. An example for a policy in India is the Gujarati reuse of treated wastewater policy from May 2018. In China, the code for design of wastewater reclamation and reuse from 2017 is another example for a regulation. Just a moment, I have case 1 and 2, reclaimed water from municipal effluents for urban and environmental reuse in Egypt and Saudi Arabia. In this photograph you can see Madinati. It's a satellite city of Cairo. It's new, very modern and green, and needs a lot of irrigation water. The water is reclaimed by secondary and tertiary treatment and disinfection. It's a simple process, but very effective. The capacity is 2 times 40,000 cubic meter a day. The second phase will be completed next year. On the left-hand side, you can see the nitrification tanks. On the right-hand side, the reclaimed water pumping station. The reclaimed water guarantee values are, for example, COD less than 50, suspended solids less than 10, residual chlorine has to be greater than 0.5, fecal coliforms have to be less than 2.2 per 100 milliliters. This plant is operated by WABAG Egypt, has been operated since 3 years, and also during the current COVID crisis, there haven't been any disturbances. Congratulations to WABAG Egypt, to the WABAG Egypt team. Mr. Yasser Okba is attending from Cairo. Congratulations. Now I come to Saudi Arabia. There is a water reclamation plant under construction. The client is Marafik Power and Water Utility for Jubail and Yambu. Contract value 120 million euro. Process as in Madinati, secondary and tertiary treatment plus disinfection, capacity 120,000 cubic meters a day. The irrigation water quality standards from the Royal Commission's Environmental Regulation of 2015 have to be met. Water reuse applications are irrigation of green areas, as in Madinati, but additionally, there is an augmentation of the subcut wetlands and very important bird sanctuary. The time schedule, the construction started in July last year. End of construction will be in April next year. The deliveries of equipment started in July this year. The status is that the progress of construction is according to this presented project schedule. 2 million safe man hours without any incidents were achieved in July this year. 2 million safe man hours means 300 safe man years. And at the plant, at the construction site, there are 1,000 people. 5 people were positive, SARS-CoV-2 positive. 75 had to be quarantined as first and second contacts, but currently there have been no positive cases anymore. So this project, the progress is according to the project schedule. I would say under these conditions, it's a great achievement. You have to imagine in summer 40 to 50 degrees centigrade. Jubail is on the Arabian Gulf, and so it's hard conditions, and it's a great achievement as mentioned, and congratulations to the project manager and his team, Mr. Srinivasan. He's attending from Saudi Arabia, this webinar. Now I come to case 3 and 4. It's reclaimed water from municipal and industrial effluents for the reuse in various industries in Chennai and Dahej in India. First, Chennai, the Coimbatore water reclamation project is located in Chennai. It's a design, build and operate contract. The capacity is 45,000 cubic meters a day. It was started up end of last year. WABAG India has got an operation and maintenance contract until 2034. The process is an advanced multiple barrier system. The reclaimed water is reused in various industries. Chennai is located on the Gulf of Bengal. It's the capital city of Tamil Nadu. The Coimbatore water reclamation plant is in the western part of Chennai, and the reclaimed water is distributed to this area. It's a highly industrialized area. For example, the water is pumped to Irongatu Kotai. There are car manufacturers located and automotive suppliers. And it's very important to save fresh water from these reservoirs. It's used only, it's now for potable water production. Last year, Chennai had a severe drought, and it's extremely water stressed. The water reclamation process, a simplified process flow diagram. We have pre-treatment, core technologies, ultrafiltration, reverse osmosis, ozone disinfection. the major design parameters for industrial reuse: total dissolved solids, 1500 in the raw water, less than 70 in the reclaimed water. In August, the current values were, the actual values were less than 50 milligrams per liter. Total silica, also very important, 40 milligrams per liter in the raw water. And the guarantee value is less than 5. The actual value in August this year was less than 1. On the left-hand side, you can see the ultrafiltration process unit. It's from the membranes from Inge company, from German Inge company. Right-hand side, reverse osmosis from Dow. It's a brackish water membrane. And you can see Chennai, a place for advanced water recycling and very water stressed. Therefore, Chennai has been selected for the next international IWA International Conference on Water Reclamation and Reuse in January 16 to 20. It's really the right venue for this next conference. I would cordially invite you to attend physically in this post-COVID event. It's organized by the IWA Water Reuse Specialist Group and Federation of Indian Chambers of Commerce and Industry. Now I come to industrial recycling in Dahej. It's in Gujarat. It's in western India. It's a plant, a purified terephthalic acid plant from Reliance. Purified terephthalic acid is a monomer for PET polymerization. PET, as you know, is used, for example, for plastic bottles. The simplified process flow diagram shows USB for pretreatment, upflow anaerobic sludge blanket, membrane bioreactor treatment is another core technology, then reverse osmosis. The permeate is directly reused for cooling tower makeup and after polishing for boiler makeup. Major design parameters, for example, COD 6,500 in the raw water, less than 1,600 after USB treatment, less than 30 is a target value after MBR. Actual values approximately 40 milligrams per liter, and in the RO permeate less than 10 milligrams per liter. TDS 2,900 and 1,100 in the RO permeate, and chlorides less than 30. On the here you can see the USB reactors, MBR aeration tanks, MBR skid, filtration cells, reverse osmosis. The membranes are from Torre. This is one example from India. WABAG India has built more than 20 such plants, and India is leading, belongs to the leading nations in industrial water recycling. And congratulations to my Indian colleagues in Chennai, Mr. Senthil Kumar, Dr. Prasad are attending this webinar, and on the west, in the west of India, in Pune, Mr. Vinod Bharati. Congratulations to all these successful plants. Also, this plant was operated without any disturbances during the current COVID crisis, and also the Coimbatore plant, which I described in the last case. Now I come to potable water reuse, indirect and direct potable reuse projects globally. I start with IPR. The difference between IPR and TPR is that IPR employs an environmental buffer as an additional safety barrier. The first 3 IPR projects are the most prominent one. Eileen addressed the Orange County Water District. They did real pioneering work in the Water Factory 21. Toirele in Belgium is doing aquifer recharge. The environmental barriers in the first 2 is the aquifer, and in Singapore, the environmental barrier is reservoirs. Meanwhile, they have 5 new water plants. Eileen mentioned also San Diego. For the first phase, the construction tenders were released in August this year. There are also IPR projects in India, at least under discussion. The V-Valley project in Bangalore. Bangalore is also very water stressed, is postponed. But IPR is also discussed in the megacities of Delhi and Chennai. Now I come to major direct potable reuse, DPR projects. First of all, I would like to mention Windhoek. They started in 1968 in the old Goreangab water reclamation plant without advanced technology. This means no ozone, no membranes. In 2002, the new Goreangab water reclamation plant was commissioned, and it successfully operated since 2002. Another project in Southern Africa is Beaufort West. They started in 2011. Big Spring blending operation in Texas. Blending operation started in May 2013. Big Spring and Wichita Falls were also mentioned by Eileen. Wichita Falls was an emergency operation from 2014 to 2015. Then last but not least, the interesting project also mentioned by Eileen, El Paso. Pilot testing has been completed. Full-scale advanced water purification facility is in the design stage. This is the water reclamation plant. And now I will present the Windhoek case. You see a simplified direct potable reuse scheme. The raw water is secondary effluent from this Gammon's wastewater treatment plant. The secondary effluent is polished in maturation ponds and then treated in the new Goreangab water reclamation plant. A maximum of 21,000 cubic meters a day is blended with treated dam water and groundwater. On an average basis, 25% of the potable water supplied to the Windhoek population is reclaimed water. Industrial wastewater is strictly separated and treated by an MBR in order not to contaminate this domestic sewage with industrial pollutants. The reclamation plant process diagram: pre-ozonation for pre-oxidation and pre-disinfection, then particle separation by coagulation, flocculation, dissolved air flotation, dual media filtration, main ozonation for main disinfection, main oxidation of micropollutants, polishing by biologically activated carbon, adsorption of residual micropollutants by adsorption on granular activated carbon, ultrafiltration for the removal of residual, let's say, protozoa, bacteria, chlorine disinfection, stabilization by sodium hydroxide. A comparison of reclaimed water quality and treated dam water quality. The reclaimed water quality is superior as compared to the dam water quality. Treated dam water quality, turbidity, for example, 0.05 NTU the dam water 0.6, dissolved organic carbon 1.7 milligrams per liter in the reclaimed water, 3.6 in the treated dam water. Why has it been accepted in Windhoek? There was no other choice due to severe water stress and lack of other cost-effective options. Transport of distant sources is 5 times more expensive than DPR. Very important. Since the beginning of direct potable reuse in '68, no outbreak of waterborne disease has been experienced and no negative health effects have been attributed to the use of reclaimed water. The city of Windhoek has an excellent information policy, and there's trust in the multiple barrier approach and technology. And the plant, the new Gorangab water reclamation plant, is monitored by local staff. This increases also the trust, and the plant has been operated during the current crisis also without any disturbances. This is essential as the water supply is secured by this reclamation plant. The maintenance is also done by local staff, so it's we can say a real success story. Now I come to the overall conclusions. Large quantities of fresh water can be saved by water reuse. This boosts the water supply security. The environmental impact, of course, is reduced. In many cases, water reuse is cheaper than other options. The undisturbed functioning of the water supply, especially during a crisis such the current crisis, is essential. This can be guaranteed by properly designed, resilient, multiple barrier processes and professional own them. And finally, it can be concluded that water reuse represents a major factor in sustainable development. I thank you for your attention.